Okay, so today we'll have a look at lesson number 2. This is a nice lesson in the sense there are two major concepts of nonlinear analysis that are covered here. The topic is incremental control techniques, and we are seeing how these two techniques, one of them is force control technique and the second one is displacement control technique. We will have a look on how they can be utilized, what is their capability, how we can utilize them to the best of our advantage to get a converged nonlinear simulation solution. So as a part of this lesson, you will also learn how to use multiple time curves, stabilize the analysis of a membrane structure, especially thin structures which are subjected to loading, use and compare these two control methods. Okay. Quick one in terms of words. First one is called as the force control method. A common terminology or verbally, if you want to understand, then this word, that is load control method, is also a nice better word to use, maybe probably to avoid some confusion on force and displacement. Typically force control is talking more towards the inputs or the forces that are being given, and displacement can be seen as the results control, that is we are controlling the results of the applied forces. So of course these are just words, but we'll have a look at how they can be changed. I said results, but the word can also be response control for displacement control. Okay, so if I see in terms of in displacement control, it can also be said a response control. And if you see these images, the first image you can see the point or the value that will be controlled is the force, the input load, and in the second case we are monitoring the displacement to control the convergence of the solution. Okay, now obviously from words it is difficult to understand, and this example is an excellent example, quite involved one, but a simple one which can help us understand this topic. So this is an example of a trampoline which is subjected to uniform pressure, and typically or as per standards these guys have to test it, and one of the testing scenarios is that this particular trampoline is subjected to a water level of I think how much is it, certain number of inches, 3 inches, yeah, 3 inches. So it is like if this trampoline is subjected to 3 inches of water, it should be safe enough, it should not break. Okay, that is the entire testing all about. So let's see how we go about it, and obviously if you want to understand the advantage of nonlinear, it is good that we get a feel of how does it behave in a linear analysis. So here is the setup that is being created. Okay, here is the setup that is created. It is a circular trampoline, and I believe we all understand that we can simplify it, and in this case we are taking 1/4 geometry. Let's take the easier setup options first. By the way, in terms of model, it is a simple cut extrude. You can see here just a extruded entity, and we are using shell. We are treating one of the surfaces to be the shell, and it is treated as thick shell with a thickness of 0.25 millimeters. Okay, this is some basic input. I believe we are all comfortable with this now. The material is nylon 6x10, and let's get into the details. Okay, so in terms of 3 inches of water, it is represented by pressure, and a value of 747 Newton per meter square is applied on the top of the surface. Symmetry conditions are given at the two edges, which are on here. Okay, and what remains is holding, so it is held at one of the circular edges over here, and I believe this is what the setup is all about. Now, in a linear static analysis on solving this setup, the results can be actually very weird. If you see here, the deflection is almost infinite, that is 2.785 E8. So there are many important topics to be understood here, but one basic fact remains is that the stiffness of this particular shell or the trampoline is very less in the planar direction, and if we do not give that initial stiffness to support the load, or if there is no stress inside the trampoline to support it, then such a behavior can be seen. And that's what we are seeing in this linear static analysis. This also tells us that we need to move to nonlinear analysis. Okay, so this is a kind of geometric nonlinearity wherein huge amount of deflection is observed, and we are not accounting for change in the stiffness over a period of time. Okay, of course. Here the results, yeah, I'm just scrolling through the text to check if anything else that I need to highlight. So if you are interested, you can of course try it with large displacement option selected. You can see little bit change, but ultimately we'll see these weird results. Okay, and a bit of explanation on why we are seeing this. This is what it is about, or such a kind of structure is also called as membrane structures. Such thin structures support out of plane loads through its membrane or in plane stresses. So that's what I'm saying. So if this trampoline is pulled in the planar direction from all the directions, all the directions, then there can be some stresses which can build up inside this particular trampoline, and that can help in supporting any perpendicular forces. And seeing the large deflections, obviously it is warranting for a nonlinear analysis, and if it is obvious that all the loads that are applied are out of plane loads. What else is important here? So now let's move on to nonlinear analysis. We are looking at what is the kind of deflection that is produced by those particular loads. So it is a simple nonlinear static analysis that is created. The shell creation remains the same. The difference comes in over here on the circular edge, where where in the past linear static we just held it in one direction. Now we are actually applying a radial deflection, or we are pulling this particular surface by 2.5 millimeter. So obviously this would create a certain amount of stretch inside this particular trampoline, and that would support the forces that are coming out in the out of plane direction. Okay, so this is applied. Other two directions are 0. What else is done? Yeah, most important is this curve. So this is not applied throughout the analysis. So as we have all understood, this is a time dependent analysis. As well, this time is pseudo time. This is not true time. We are using it to apply these loads. So in this case, from a time instant of 0 to 0.1, this stretching is done. That is, it moves from 0 to 1. Thereon, from 0.1 to 0.5, we keep it flat. It is maintained. And finally, when we move from 0.5 to 1, we are moving from 1 to 0. That is, we are basically releasing the trampoline to its original state. Okay. By this time, that is somewhere around 0.1, we start applying the out of plane water load. That load will have its own effect and will also start creating its stresses inside the system. So this is one primary big thing that has been done, or the difference. Symmetry remains the same, no difference. Pressure is the same. The rest of the things come in the properties of this study, where we are defining a few different things. Now the default number of adjustment is 10. I believe by now you all know what is number of adjustments. So typically in this case there are high chances of solution failure or convergence, and the solver might try to step back a little bit to try to converge with a smaller force load. We obviously cannot stop and do these changes manually, so we are keeping it with an automatic option, wherein in case the increment has increased, it will automatically drop down. As well, to help convergence, we are increasing the number of adjustments that is permitted. Okay. Second thing, of course this is a large displacement formulation, so ensure you have selected that, and the solver is direct sparse, that's fine. And in terms of control methods, of course this is the default one, but that is what we are looking at here. We will use the force control algorithm over here. Newton-Raphson integration method remains the same. What else is important? Yes, one thing which I would like to highlight here, the update load direction with acceleration. Okay, this typically or logically we might say that it needs to be selected, and the trampoline needs to be, or the force on the trampoline is changing with the change in directions. But the reality is, because this is water load, it is well distributed on the surface, so it is actually acting perpendicular. That is, it is kind of a gravity load which is always normal to the, not normal, it is always how can I say, in a particular direction which is referring to the direction of gravity. So keeping also not changing the direction of these forces is fine and is acceptable. Okay, so that's how it is, and it would look something like that. We can what else is required? Yeah, so this defines the setup. After you run the analysis, and when we see the results at the end of the analysis, we can see the deflections are not infinite, but they are in the tune of 191 millimeters, and if we probe the result at the center down here, okay, let me try to do that over a period of time probably. So you can see the variation that tells how it is going, and of course in this case the graph is something like that, and that tells us how it looks. Okay, now yeah, of course the option is somewhere here, but I think I would like to look at some more details in the PDF. Let me check if I missed out on any other important topic. So we copy the linear settings as it is, and we copy the linear settings as it is. The force is linear from time instant 0 to 1, and that's what is maintained. Set properties of non-linear force control study 1 to 0.8, that is fine. Set the max time to 0.1. Yeah, that is all. That is the default one rather. Yeah, I missed out. Actually, in the training manual, we actually try to solve it with a number of adjustments of 5, and thereon we see a failure, and then we actually increase the number of adjustments to 10 and try to solve it again. So this is fine. The update load direction I discussed. Newton-Raphson is fine. This is what we are doing. Yeah, as I told you, we'll solve it with this. You will see a failure, and this is typically initially where it is trying to converge. In order to display the failure, of course, we may not even use the translation to be or initial stiffness of 2.5 millimeters and have a look at it, but that is just to show you how the changes are going to happen. Yeah, this is done. This is 0 to 1. We are applying the load, and the load is how much? So both the load, I'm not sure if I showed you this. So even this particular pressure value is using a curve, using a curve, and you can see here it is varying from 0.1 to 0, and at 1 we are moving on to a value of 1 unit. So this I think I had missed out. Apart from that, pressure is same. Yeah, so the other change will be the number of adjustments to increase here, and typically this is rerun. In case you are not aware, we have this option of restart over here. So if you want to do any changes to the setup, especially in the property manager, and get back on the analysis from the previously failed run or intentionally stopped solution, then you can do that, and that should help you proceed with it. What remains? Yeah, of course you can see the solution while it is running. In case you are curious, I can also trigger it down here. It looks nice in the sense, especially once we implemented this option of dynamic update of the results, it is truly different. In the past, obviously, we didn't know what is happening in the background, and it was really meaningless to see. It was just these bars that were moving, but now with the solution, we can actually visualize the variation of results. Yes, it is the final step, true scan, all in there. Okay, so this is what it is. Let me check plot displacement results. 1 second. Yeah, this we saw. By the way, there is a analytical equation as well for solving such membranes. Or you can as well use it and try to compare the results if interested. Okay. We probed the midpoint, that's what we did, and we saw at around 1 second the displacements are in the tune of 190 millimeters, which corresponds to 33% of the load. So at around T is 0.04, which is almost 33% of the load, that is 247 megapascals, which is in the tune of 104 millimeters in displacement. Now obviously the question is this value indeed the displacement at 33% of the load? Okay, this is an interesting topic. You might want to think on it, on if this is the true displacement. If you remember, we did some initial pulling of the stretching of the part as well to help in certain cases, certain stability, so that might have changed, but that's what it is. Give a thought. This is an interesting point that has been made here on if this displacement of 104 that you see here, is it the true displacement? Should it be considered or should it not be considered? Now the same question, wherein we knew the amount of force that is applied and we are trying to understand the displacement, is reverted, or we are thinking that how much force would be required to deflect the trampoline by 200 millimeters. In this case, we are looking at something called as nonlinear, the same nonlinear analysis, but using the displacement control method, and that's what we will see now, the way it is approached here. Now here a kind of different problem comes in, wherein we cannot apply that initial stretch of 0.25 millimeters because this particular solver does not allow giving force displacement. So typically all the displacement should be 0 in this particular analysis, and I believe apart from other things, if we just think in the form of common sense, wherein we are saying we are controlling the displacements here or the result, so obviously the software does not permit us to give it as an input as well. you can think in that direction. Of course, it is true for all such solvers. And because of that, we cannot use that for stabilizing the model initially. So one of the changes that happens in this setup is that one, wherein we are changing. So all other things remains the same. If I go in over here, in terms of properties, one of the things that it changes is number of adjustments. So because we are not giving any initial stiffness to the trampoline, by stretching it, we can expect instability, and increasing the number of adjustment to 15 should help over here. Under advanced options, we are selecting the displacement algorithm. We are selecting the point which is at the center down here as the vertex for controlling, or the displacement for controlling. We are controlling the UZ translation, or we are monitoring it, and it is controlled using this particular graph. We are looking at a deflection of around max deflection of around 200 millimeters at a time instant of 1. Displacement variation with time, so the graph might look something like this. So we are kind of controlling this displacement to see how much force is coming. So it is exactly the reverse or reverted approach. All these remain the same. Any other changes down here? No, all others except incrementing it to 15. So this immovable translation has been changed, and the force displacement has been removed, and it is all 0 down here. Okay. Symmetries remain as it is. Pressure, again we can set it back to 1, because here again we are controlling. This pressure is applied just to tell where the forces are being applied, to to tell the solver yes the location of loads. And thereon the software can tell us what is the maximum load or the factor required to achieve a certain amount of displacements. Okay, so this is how it looks. This is the a displacement control algorithm, and at the time instant of 1, of course we are forcing this, so we are looking at around 200 displacement. But if you plot the graph, that will give a clear idea of where it is. So we are looking at a displacement of around, or if I say if it is to be compared with around 191 from the previous analysis, it would be somewhere here, which can correspond to the same value of around 747, which is multiplied by 1 pascals, which we apply. So nothing but 741 Newton per meter square could be the force or the pressure that is applied, and we are getting these similar results. But the rationale or the logic is we got similar results using 2 different methods, 2 different logics, and that tells us how these 2 algorithms can be used to your advantage, and how we can use them to the best to help in good convergence. So this is what it is. Let me check if this text has some more content which I have missed out. Okay, this particular graph, okay, that's it. I think in this chapter that we learn. So yeah, some minor manipulations have been done in the way this graph is shown. If you want, you can explore it. We are also looking at exporting this graph into an Excel sheet. Okay, and yeah, pretty much that's it. So as you saw, we saw how do we use these 2 algorithms of force control and displacement control. Force control is also called as the controlling the loads, and displacement is more towards controlling the results. We are using these 2 algorithms to control the convergence of a solution, and we saw how effectively they can be used to our advantage. Okay, so this is it all about. A few good questions. The answers are there in the previous text that we went through. They should help you there. Any questions, any doubts throughout this lesson, feel free to call me, feel free to email me. We can have a chat on that topic. Okay, thanks a lot. We'll catch up in the next lesson, which is lesson number 3.